Hello, everyone. Now, a nice, very interesting topics. One that I adore: the least squares method. The idea in this section is that we're going to be looking at system of linear equation with no solution. When you think about it, if you've done enough practice solving system of linear equation, normally solving a system of linear equation with no solution feels like a waste of time. But actually, in practice, when you're trying to solve a system of linear equation that comes from real data, you rarely have a perfect solution for your data. And what you're trying to do is find the best possible solution. And what I really enjoy in this section is that it uses things that we've seen before to construct that perfect solution. And it fully justified the time that we spend on those things nicely. So, what is the least square method? So, first and foremost, the goal here is to study system of linear equation with no solution. So, there's no solution for this system, but we're trying to find the best possible solution. So, when possible, what we're going to do is find the best possible solution, the one that we call the least square solution. And how do you find that best possible solution? And this is where all this very rich matrix structure behind our system, like the coefficient matrix and the augmented part, will be very, very useful. So here the idea is that the method is you construct this new system that is called the normal system. So you have your system of your equation, you know your coefficient matrix is A, you know the augmented part is B, and what you do, you multiply both sides of this system of linear equation in matrix form by A transpose. So on both sides, you multiply by A transpose. So you're starting with AX equal B, and on both sides, left and right, you multiply by A transpose. So in other words, this new system, the coefficient matrix of this new system is no longer going to be simply A, it's going to be A transpose multiplied by A, and the augmented part, so the augmented part is going to be A transpose times B. And what's interesting here is that even if you start with any system, because A, for example, could be M by N, every time you multiply A transpose by A, you're going to get A transpose, the size is going to be N by M, and A is going to be M by N. So this multiplication is always going to be defined, and the result is always going to be a square matrix. And that square matrix, A transpose times A, is always going to be A M by N by M. So here, that matrix is always going to be a square matrix. And of course, for us, for our applications, that square matrix is going to be a 2 by 2 or a 3 by 3. So just a small concern here when I say when possible, when is this possible? So there is a limitation, but for sure, if you compute the determinant of A transpose times A, remember this will be a square matrix. If you don't get zero, so if the answer is something that is not zero, for sure, there's a best possible solution. So again, here I want to be clear. This is really algorithmic at this point. I'm just saying, hey, there's no solution. Multiply by the transpose. Make sure that the determinant is not of A transpose times A is not zero. I'm not giving you the origin story of that method. It is rooted in linear algebra. But if your goal is just to find that best possible solution of that system, AX equal B, no problemo. Just multiply by A transpose of. All right. That was Atari that did not like the arrival of the postman. Dowie, calm down, baby. All right. So, yeah. So, so no worry. Just multiply by A transpose on both sides, get that square system, and then solve that square system. And you are masters now at solving square systems. You can either use the inverse if your square system is a 2 by 2, or you can use Kramer's rule if the system is given by a 3 by 3. All right, so let's look at our first example. Very classic example. Um, So we want to find, so my first example here, we want to find the equation of the line y equal mx plus b. So here we're trying to find a line. So the unknown are the slope and the y-intercept. So we're trying to find that best line that passes through the following point: minus 370, 121, minus 7, 100, and 5, minus 35. Just to show you what we're trying to do here, I have for you as a remark. So just at the end, this is not really part of the solution. This is more like a, a little visual remark for us. So I'll draw that little eye here. So just a visual remark. If you plot these points here in red, so if you plot these points given in the question, these points are not perfectly aligned. So there's no linear equation. There's no perfect equation mx plus b that fits through this data, but you can see that these points are fairly aligned. And of course, here I have that black line, which will be the perfect fit. But how do you find that perfect fit, or that best possible fit? Sorry, not that perfect fit. Well, we can do it using the least square method. So here we go. So we're trying to find m and b. So the solution here, the first thing you should do is just understand, because be careful, because we're trying to find the equation of a line y equal mx plus b. You're so used to use x and y as the variables, but here the unknowns, the variables, and take the time to label that. So what, like when I say give me an equation of a line, what is missing? It's the slope, it's the value of m, and the y-intercept b. So let m be the slope of that line and b be the y-intercept of that line. And the goal is to find those two quantity. So what we have here, we have 4 points. The trick is fairly simple. How do you build that system of linear equation in terms of m and b? Well, for every single point, you plug that point in that equation, and then this gives you an equation. For example, if I plug minus 3 in my equation, so mx becomes m times minus 3 plus b, we don't know what b is equal to y, where y is 70. So my first point gives me my first equation. So for every single point, you get an equation. Then you plug it again. So we also want mx, where x now is 1, plus b is equal to y, where y, the second y, is 21. So that's for my second point. And then again, you replace x by minus 7 and the y by 110. And that gives you your third equation. And finally, replacing x by 5 and the y by minus 35 gives you your last equation. So remember here, the unknowns are m and b, not x and y. So when I look at the augmented matrix of this system, the coefficient part, so the coefficient in front of m are my first column. So I can see here that minus 3, 1, minus 7, and 5. And then all the b's, because it's plus b no matter what point you're using, the coefficients are always 1. So you're always going to get a 1 in the second column when you're trying to find the best possible line. And then the augmented part are given by your y coordinates of my 4 points. And here, if you do it, if you do apply Gauss-Jordan, you can verify that the augmented matrix of that system will have a pivot in the augmented part. And because there's a pivot in the augmented part, there's no solution. These 4 points are not perfectly aligned. There's no solution. But we want to find the best possible solution. So normally, if you don't know about least square, you would say, oh no, the system is incompatible, and you would just cry in a corner forever. But now we're better equipped. We're going to be building the normal system. So the advice here that I have, always label nicely from your augmented matrix. What is the coefficient matrix? In this case, it's A here in the augmented part. So label that correctly. So here, when I'm building the normal system, make sure you know where the coefficient matrix comes from. So the matrix A and the augmented part, and write it as a column matrix or as a vector. So you have those two coming from the augmented matrix. And now you have to compute A transpose times A. So remember, This is actually a computation. So if you need some detail here, so make sure, and this is why I love these questions, because there's a transpose in that question and there's a matrix multiplication. This is a perfect question to see if you know a bunch of different things. So remember, A transpose is simply going to be, if I transpose here, A, my first column will become my first row. So you get minus 3, 1, minus 7, and 5. And then so remember, so first column becomes the first row. And then the second column becomes the second row. 1, 1, 1, 1. Okay, so that one is easier. So here's my second row now. And make sure you know, okay, so that's my A transpose. And if you multiply it by A, so minus 3, 1, minus 7, and 5, 1, 1, 1, 1, okay, that you get indeed the matrix 84. So it's square. So by the way, here's a little size analysis. This is a 2 by 4 multiplying a 4 by 2. So this matrix multiplication is defined, and I know the size is going to be a 2 by 2. If you do it, good exercise here, verify that you get 84 minus 4 if you make this first column fall on the 2 rows. And then if you take the second column and you make it fall on the 2 rows, you're going to get minus 4 and 4. So make sure you do it. Feel the matrix multiplication here. And then for A transpose times B, again here, just to be super explicit, just to show you everything that is going on here. So I have my A transpose again, and now I'm just multiplying it with B. So where B is 70, so 70, so 70, 70, yes, 70, 21, 110, and minus 35. And when you do your multiplication, double check. First, this is well defined. This is a 2 by 4, and you're multiplying a 4 by 1. The result is going to be a 2 by 1, and verify that this gives you minus 1,134 and 166. And those are your new coefficient matrix in augmented parts. So you get your normal system. So your nice normal system, the coefficient part is A transpose times A, and the augmented part is A transpose times B. So here's my A transpose times B. Here's my A transpose times A. And then you solve it. Of course, here, because I've done things on the computer, I've used Gauss Jordan, but my advice for 2 by 2, this is absolutely precious advice here. I'm even going to change the color just to make it more vivid. But if I was solving this system of linear equation, if this is my square system of 2 by 2, what I would do is I would compute the inverse, because this is a nice 2 by 2. I would compute the inverse of that coefficient matrix, which is A transpose times A, and then multiply it by the augmented part. And what is the inverse of a 2 by 2? So the goal here is when you're computing the inverse, you take your 2 by 2, you just switch the elements on the diagonal very quickly. So the 4 and the 84 change spot. The other elements, they just change sign. So minus 4 will be plus 4. Same thing for that corner. And then I need to multiply everything by 1 over the determinant. So if I draw my little fishy, so let's just draw the little fish here. Where's my fish? So if you draw the fish here for the determinant, 84 times 4 minus 4 times 4, so you get 84. Wait. So 84. So 84 times 4. Let me just write this determinant a bit here. Anyway, so 84 times 4 minus 4 times minus 4. So minus 4 times minus 4. Not doing the computation here. I'm just showing you one way to do it for yourself. So when you take this coefficient and you multiply it inside that matrix where you change A and D, their spots, and you change the sign of B and C, and you multiply it by the augmented part, in this case, minus 1,134, and then 166. When you do the actual multiplication, verify that this gives you a very nice clean, minus 12.1 and 29.9.4. Remember what these numbers are. Okay, so that's your value for M, that's your value for B. So what you're getting at the end is the equation of a line where the slope and the y-intercept are no longer unknown. They're perfectly understood now. So the equation that fits best this data is y equal minus 12.1x plus 29.4. And again, visually here, this is not part of the solution. It's just to show you what this line is. So if you draw that line with the y-intercept at 29.4 with a slope of minus 12, so if you draw that line and you compare that line versus the data, it's the best possible fit. So it's absolutely amazing. So for me, like, especially as a teacher, I want to show you a nice application of linear algebra. You've probably, well, hopefully you've been exposed to data before which had a linear trend. You probably computed the best possible line, which we call regression theory or regression analysis. I'm not sure about the terminology in English, but you get the idea. Let's try to find that best line. You probably had a bunch of formulas to compute that. These formulas, the origin story of these formulas are rooted in linear algebra. Again, disclaimer, I'm not showing you why this is working. We would need a little bit more theory to explain that, but actually the proof is rooted in very nice geometric arguments that can be explained with a little bit more advanced linear algebra. But for me as a teacher, a question like this requires what? Requires that you build your own system of linear equations so that you label correctly the matrix A and the matrix and the augmented part B. And then as soon as you understand that there's no solution, you can take A and transpose it. So that's a perfect way to check if you know how to transpose correctly, or a perfect way for me to check if you know how to transpose something. Then there's a bunch of multiplication, A transpose times A and also A transpose times B. This will give you a square system, and then you have to solve that square system for 2 by 2 using the inverse is the best way. And if you have a question that leads to a 3 by 3, the best way to do this is by using Cramer's rule. And my advice, I'm not going to go through this example in the video, but as an exercise, try to do the next question. Now, the question is slightly harder. We're trying to find the best quadratic equation that fits through those 4 points. Again, it's good to see what we're getting at the end. We have 4 points that are no longer linear, but we're trying to find that best possible quadratic. So when you're looking for a quadratic equation, what you're trying to compute, what you're trying to find is the coefficient A, coefficient B, and coefficient C. So you're trying to find the best possible solution, the best possible quadratic equation that passes through those 4 points. So for every point, you get an equation. In this case, again, if you try to solve that system, you will not get a solution because these 4 points are not aligned quadratically speaking. So, but you want to find that best possible quadratic, label A, label B, construct A transpose times A, construct A transpose times B, construct that normal system. And this one, if you want to do it as an exercise, the best way to get the best possible solution of that square system, because it's a 3 by 3, use Cramer's rule. Anyways, I'll let you work on it on your own. It's a very nice example. But for me, for that section, that's it. That's all. Bye-bye.